We finished chapter 4. We also did the tutorial number 9, and we solved all the questions. Some of them are skipped, and I labeled that. Okay. So before we start today, we will have quiz at 3. Maybe I should put a reminder. Okay, after the lecture. Okay, chapter 5. This is our last chapter in this semester. It's about system, vibration of system with 2 or more degrees of freedom. Okay, in degrees of freedom, we talked about this in chapter 1. We measured the number of coordinates, the number of independent coordinates in a given system, and that's equal to the degrees of freedom. So what we did in chapter 2 up to chapter 4 was about vibration of single degree of freedom system. Okay, in chapter 2 it was a free vibration, chapter 3 was about harmonic excitation, and chapter 4 about transient vibration. All of the previous sections, chapters were about single degree, in which there is only one variable. And the systems that we analyze in those chapters were either translational system or rotational system. In 2 degrees or more, this is the name of the chapter, 2 degrees or more. So we will, 2 degrees means we have 2 independent variables involved in the system that are required. And the main thing is that 2 independent. Okay, if you go back to introduction we did in chapter 1, chapter 1, lecture. Okay, here we talked about degrees of freedom. Okay, and we said the number of independent coordinates required to describe the motion of a system is called degrees of freedom of the system, and then it's a single degree of freedom, and there is 2 degrees of freedom. Okay, so 2 degrees of freedom, we have 2 masses which are moving with 2 different coordinates, x1 and x2, which are independent. Or you have rotational system, θ1 and θ2, which are 2 independent coordinates. And of course, you have more 3 degrees of freedom, and then up to if you have a continuous system. Okay, when you have 2 degrees of freedom, it means you have the system has in free vibration will have two nature frequencies. If the system is 3 degrees of freedom, then there will be 3 natural frequencies. So the number of natural frequencies in the system equals to the number of degrees of freedom. And what we did so far, it was only one. There is only one natural frequency. We call it omega n. And that is the only frequency, because single degree of freedom system will have only one natural frequency. So as a rule, it will be the number of natural frequencies involved in the system is equal to the number of degrees of freedom. And as we define degrees of freedom is the number of the independent coordinates. In free vibration, this chapter will involve the 2 parts, the free vibration and force vibration. And it can be force vibration is the harmonic excitation, or it can be also the base, the transient vibration. You can put all what we did so far and generalize it on a system of 2 or more degrees of freedom. Okay, 2 or more, it means sometimes it's called multi degrees of freedom system. or in degrees of freedom system. And the more the number of degrees of freedom, it is more the complexity of the system. Let's say in analyzing, in finding the nature frequencies, in finding the response. So we will talk about 2 degrees of freedom, but you can extend the method that we are going to use to more than 2 degrees of freedom, but you will need to use, computer. Up to 3 degrees of freedom, you can do it with hand, but when it is more than 3, you need a computer to do the analysis. Okay, so we have that number of nature frequencies equal to the number of degrees of freedom. And there is one more thing we will talk about here in the free vibration is, just if you will recall what we did in chapter 2, we will find the nature frequency after we find the equation of motion, right? And then we can find the response if initial conditions are given. Here, before we talk about the response due to initial conditions, we will, beside what the nature frequencies, we will talk about, called mode shape or normal mode. Okay, so as you can see in this paragraph, that for each of the nature frequencies, there correspond a natural state of vibration with a displacement configuration known as normal mode, and sometimes we call it mode shape. Okay, mathematically called eigenvalues and eigenvectors. You might recall this from linear algebra, that if you have system of equations, you can find eigenvalues and eigenvectors. Eigenvalues correspond to the natural frequencies. Eigenvectors correspond to the normal mode or mode shape. So this is the extra thing we have in this chapter for 2 degrees of freedom or more, that besides the nature frequencies, we will find the mode shape associated with each frequency. Okay, so to illustrate what I mean by normal mode, I will give you an example about continuous system, although this is not related to multi degrees of freedom. It is continuous system. The way to solve and analyze the resulting vibration of continuous system is different, but the mode shape is, maybe I can best describe it using a continuous system. In a continuous system like beams, if you have a similarly supported beam, and this is under vibration, this can take vibration in different modes. First mode, this is the, let's say, equilibrium. This line is the equilibrium position. No vibration here. And it can vibrate as a first mode. It means that the whole beam will go above the equilibrium line or below the equilibrium line. I mean, it will vibrate between, above and below the equilibrium line. This is called first mode. First mode shape or first normal mode, in which as you can see, all the points, the beam, it's all the point on the beam is vibrating above and below the equilibrium line. Okay, and this occurs at omega 1. Okay, omega 1 is the natural frequency. The second mode, it will oscillate similar to a sine wave. This is the first mode, like half sine. This is the displacement of the beam, and this is related to the length of the beam. Okay, and measured, let's say if you measure x from here, this is y, and this is x. So this value of y is dependent on x. Okay, the second mode, we will have a complete sine wave. Okay, either this way or this way. This is second mode. And we have here sine wave. And this is when the beam is vibrating with the second natural frequency. Okay, this is called first natural frequency. And this is called second natural frequency. And we have always omega 2 is greater than omega 1. Omega 1 is the lowest frequency, and so on. So this will complete this. There is no end to this because this is a continuous system. Continuous system has infinite number of degrees of freedom. Or it will vibrate this way. Okay, and so on. So this is omega 3 here. This is third mode, and so on. And omega 3 is greater than omega 2. Okay, so omega 1 is called fundamental or lowest natural frequency or fundamental. Okay, so what you need to do is if you have discrete, this is a continuous system. So this is example of mode shapes. Of continuous system. Okay, this will continue to infinity. Now, if you have a discrete mass system, then the mode shapes natural frequencies will equal to the number of degrees of freedom. So for discrete, mass parameter system, okay, number of modes will be limited, of course, equal to number of natural frequencies. So if you have for 2 degrees of freedom, okay, let's say spring mass system like this. So there are 2 coordinates only, and then there will be 2 nature frequencies. Not open as the continuous system. And accordingly, there will be 2 modes. Okay, the modes, and we will see how we can obtain nature frequencies and also the modes. But this is discrete. This point is always displacement. Here is 0. This is fixed, right? And this is also fixed. As you can see in the similarly supported beam, this is a fixed point. So displacement is always 0. And this is also fixed here. So displacement is always 0. So what you see here with the red lines, those are the displacement, deflection, or configuration. So at this point is always 0. We say y is 0 here, and y is also 0 here. And you can see this is also y equal to 0, this point. There is, in the first mode, there is no y equal to 0 in the, along in the middle, yeah, between the ends. Here, for the second mode, there is y equal to 0, and it's called node. Okay, here we have 2 nodes. And if you go to mode number 4, you will have 3 nodes and so on. Nodes means 0 displacement, y equal to 0 all the time. All the time. It is vibrating with this mode. It means that all the time those nodes will have 0 displacement. That makes the beam and their very complicated geometry and displacement. Make bending and loading will be very complex. The same thing can happen here, but assuming that the variation in the spring is linear, 0 from here, maximum here, x1. So the first mode of this vibration system, 2 degrees of freedom, if you draw the 0 line, this is the equilibrium line. This is always 0 displacement. Y is 0 here because this is fixed. Y equal to 0 here. Okay. If x1 and x2 move in the same direction, maybe one smaller than the other one. Okay, I can just assume that that's what we will get. So there is no node here. Okay. So this is the deflection in the spring, and this is the deflection in the spring in the middle, and this is the deflection in the spring in the third spring. And this is the location. This is y or x1, and this is x2. And there will be second mode. We will see how we can obtain the second mode and the first mode as well. Again, we will have 0 displacement here, y 0 and y 0. And this will have a point here and a point here. Okay, so it will be either the same thing for the first mode. Okay, so it is either minus x1, minus x2. Here we have x1 positive, x2 is negative. There is node. Okay, so this is details, but we can, as I told you, maybe with the continuous system, it is easier to understand the modes. Okay, the same thing for discrete, and we are going to do only discrete system here in chapter 5. Okay, the method we will use is called normal mode analysis. Okay, it is the basic method of determining the nature frequencies and mode shapes of vibration. Simply, if you have in this example, this example number 1, we have M1 is M, M2 is 2M, and we have K1, K2, K3 are K, K, and K, they are equal. And we have the coordinate X1 and coordinate X2. Those are 2 independent variables. So what you do, assume that the vibration will be harmonics for X1 and X2. Okay, so first of all, you find the position or the direction of the X1 and X2 has to be defined in one direction. Let's say both of them positive to the right. Okay, and then we take the free body diagram. We do the free body diagram on each mass. We have for the mass on the left, which is moving with X1, we have this spring will be under tension. And the spring in the middle depends on the assumption of X1 and X2. Usually we let X1 greater than X2, so the spring becomes under compression. And the spring here will be under compression because it is fixed on the other side. Okay. Then you draw the free body diagram, okay, with the assumption we did here. And the direction of X1 and X2, then you can say this is under tension, the spring in the middle is under compression, the spring at the end to the right is under compression. So you draw the effect of the forces on the mass in the direction of the vibration. So we have Kx1 to the left and Kx1 minus X2 is to the left as well. And this is on the second mass. The force is in the opposite direction. So this is action and reaction. And the spring on the right hand side of 2M is also to the left. And then this direction is positive, to the right is positive. Equations of motion are obtained by, you consider.
عندي سؤال دكتور.
اوكي تفضل.
دكتور ليش ال 2M هذه صاير كمبريشن او بوتنشن؟ المفروض تنشن دكتور. اشوفه
هاي السبرينج؟
السبرينج اللي في النص دكتور.
سبرينج اللي في النص. اوكي. Okay, this is depends on the assumption. If you assume that X1 is greater than X2, what will happen to the spring?
دكتور هو مو بيتحرك لليمين لأن 2M أكبر.
إيه. Okay, so this is the spring without before it's in equilibrium. Okay, when you say that X1 is greater than X2. Okay, this is L0 and this is L1 or L. Which one is bigger, L1 or L0?
L0.
Yeah, so it is under compression. Okay, because this point is moving with a greater distance than this point. That will get shorter. And then when it gets shorter, it means under compression. Okay, so when you apply Newton's second law, sum of forces equal to M on mx1 double dot, and we take this direction positive. We have mx1 double dot equal to minus kx1 minus, okay, I will do this here, equal to minus kx1 minus kx1 minus x2. Which can be, I don't know why he used the plus, because if you take the minus inside the parentheses, this becomes minus kx1 plus kx2 minus x1, right? They're the same. They are the same. There is no changes here. And you use the sum of forces equal to 2m x2 double dot. Again, you take this direction positive. You will get k m 2m x2 double dot equal to k x1 minus x2 minus k x2. Okay, again, he flipped the sign, but this is the same. 2m x double dot, I'm reading his equation. 2m x2 double dot equal to minus k x2 minus x1, which is same as saying plus k x1 minus x2 minus k x2. Okay, those are the two differential equations which we need to solve. Okay, those are ordinary differential equations, but with two variables. Okay, for the normal mode analysis, and for the normal mode of oscillation, each mass undergoes harmonic motion. Okay, that's the assumption for normal mode analysis, that each mass will vibrate with a harmonic motion of the same frequency, passing through the equilibrium position simultaneously for each motion. Okay, so what is the assumptions here? That we write x1 equal to a sine omega t, where a1 is the amplitude and omega is the frequency of oscillation, and x2 equal to a2 sine omega t. This will have amplitude different than x1, a2, but the frequency is the same. Now, is this physical? Yes, it is physical. That if you have a system, those are joined by spring. The two masses are joined by series of springs, so they form one system. They are not two separate systems. Okay, again, if I take a continuous system, maybe that's easier to understand even for, let's say, a cantilever beam. Okay, if you vibrate, if you put a force here with a sine wave or whatever, okay, then it will vibrate with a frequency omega, this point. Okay, it will vibrate up and down with the frequency omega. How about the other points? They will vibrate with the same frequency. Okay, otherwise, you know, imagine that this is not fixed. Okay, maybe if you have a take ruler, okay, and excited by your hand on this side, okay, up and down with the frequency omega. So the whole beam, the ruler will go up and down with your hand, right? With the same frequency. So let's say this 0.1 and 0.2 here, let's say 0.2 here and 0.3 here, they will all vibrate with the same frequency. They might have different phase. That means one point will go up, other point will go down, but the frequency of oscillation is the same. Unless the beam is not forming a continuous system or okay. Okay, unless that we have two beams. If you have two beams, then of course, and they are not coupled, then of course, if this is vibrating with omega, I don't know what is this, why vibrate. It can vibrate with any other omega. It's separated. But once you have a system that is joined together either by springs or it is a continuous system, all the points on the system will oscillate with the same frequency of excitation. So for the discrete mass system, any point you take on the spring, on the mass, on the spring in the middle, on the mass, second mass, they all vibrate with the same frequency. They might have different phase. They lag, but that one will be leading, other point will be lagging, but they oscillate with the same frequency. Okay, that is very important. And this idea is, we can prove it mathematically as well. And we will see that. So here, that omega is the same. There is no omega for M, and there is no different omega for 2M. We have two masses, right? So there is no omega 1 for M1, and there is no omega 2 for 2M. That is not true. The whole system is vibrating with the same frequency, either with omega 1 or with omega 2 or with both omegas, but at the same time. All the points on the system vibrate with the same frequency. So this is why when you write the amplitude displacement of M1 as a sine wave, it is A sine omega t, and x2 is A2 sine omega t, which means that the two masses can vibrate with different amplitude, but not with different frequencies, the same frequencies. Okay, so this is the procedure we did before. You can use sine or cosine, or as mentioned here, you can use the complex form, which includes sine and cosine. So this is A1 cosine omega t plus I sine omega t. The same thing here. So anyone who uses, okay, so since we are familiar with using sine terms, we will continue with the sine terms. Okay, with this assumption of x1 and x2, we'll substitute in the above equations, differential equations. Okay, so we get the second derivative of x double dot. You know, we have equations, there is x double dot, so x1 is a1 sine omega t, and omega 2 or x1 double dot becomes minus a1 omega squared sine omega t again. Okay, the same thing with x2 is a2 sine omega t, and x2 double dot, which is in the equation, will have minus a2 omega squared sine omega t. Now let me show you that if you substitute with different omegas, there is no solution with different omegas. So for example, the equation of motion is, I will substitute in, if you assume that x1 is a1 sine omega 1 t and x2 equal to a2 sine omega 2 t, and then substitute in the first equation, you will get minus m a1 omega 1 squared sine omega t, sine omega 1 t, equal to minus k a1 sine omega 1 t plus k times a2 sine omega 2 t minus k times a1 sine omega 1 t. I just expanded the bracket, open the bracket. Now what you will do, you collect similar terms, sine omega 1 t terms, which are minus a1 m omega 1 squared, okay, equal to minus k a1 minus k a1. Okay, so you can see that okay, if you take this, then if you take the sine omega 2 t, you get 0 on the left hand side, equal to k times A2. Okay, which is not does not make sense because this makes A2 equal to 0. And that also this equation will be not have no meaning because you cannot find A1, you cannot find omega 1. Okay, so the only way that mathematically this will be true is when x1 and x2 are moving with the same frequency. They can be of the same, I mean, different amplitude, but of different frequencies. Otherwise, the equation will not be balanced. Okay, so using this assumption of x1 and x2, this is true, and this is correct. When you substitute, you can see that omega t will cancel out. Okay, omega t when substituted in the first equation will cancel out, and you get 2k minus omega square m times a1 minus k times a2 equal to 0. And the second equation will give you minus k a1 plus 2k minus 2 omega square m times a2 equal to 0. Those two equations. Okay, and I think you can just try. You can exercise this yourself. Substitute in the first equation. You will get minus m a1 omega square sine omega t and so on. You will see that sine omega t will cancel out. And then you can collect similar terms of, you take a1 as a common factor, and you collect terms that contains a2. In the second equation, you do the same thing. You start with a1 and put the first term as a1, and then the second term as a2. Those two equations to be solved together. Now, if we count the number of unknowns, what are the unknowns here?
A1 and A2.
Okay, A1 and A2, and what else? And omega. Remember, the free vibration, it means to find the initial frequency. Okay, A1 and A2 are also unknown. So there are 3 unknowns with 2 equations only. Okay, so let me put this in those 2 equations in matrix form, and then you will see how we can get the solution. Okay, putting in matrix form, this is the
دكتور هذه الأوميجا excitation frequency.
Yeah, this is the free vibration, as you can see from the.
Okay, doctor.
This is the initial frequency. Okay, but here we are not saying omega n because we have more than one natural frequency. So we omitted n and we will use omega 1, omega 2. Okay, now it is omega, which means the initial frequency. Okay, so here with the assumption that omega is the natural frequency to be found. Okay, this is the main unknown here we have. A1 and A2 are also unknown, but the main thing is we need omega. Okay, putting the 2 equations in matrix form, you can see that when you multiply the matrix, this is 2 by 2 matrix, and this is 2 by 1, 2 by 2. This will give you the 2 equations that this 2k minus omega square m times A1, which is the first term here, minus k times A2, which is the second term, equal to 0, and the same thing for the second equation. Okay, in the matrix form, it is equal to 0. Then if A1 and A2 equal to 0, this is valid. That's the equation is satisfied. Okay, so for A1 equal to A2 equal to 0, the solution, this is a solution, but the solution is not the one we want. The solution is called the trivial solution. So what is the other solution? The trivial solution means there is no vibration. That if A1 equal to A2 equal to 0, there is no vibration. Or we put the determinant of the matrix equal to 0. Okay, that is the second solution. Determinant equal to 0. And determinant of 2 by 2 is we have, this is the determinant, 2k minus omega square m minus k, 2k minus 2 omega square m, and we set the determinant equal to 0. Okay, the determinant will be multiplying this term by this term, which will be 2k minus omega square m multiplied by 2k minus 2 omega square m minus, you multiply this by this with a minus. This is a plus. So minus and minus becomes minus. Huh? Minus k times minus k is k squared, and there is a minus, becomes minus k squared. Okay, this is the determinant with one unknown, which is omega. So if you expand the equation, if you expand this will be minus 2m squared omega to power 4, and you multiply the inner terms and the outer terms, we'll have minus 2km and minus 4km. It means minus 6km omega squared, and and 2k times 2k is 4k squared, and minus k squared becomes 3k squared. If you divide by 2m squared with the minus, you will get omega to power 4 plus 3k over m, okay, omega squared plus 3 over 2 k over m squared equal to 0. This is in terms of minus. Yeah, minus. Maybe there is, I have a minus term. Okay, this should be plus. This is my mistake, because minus multiplied by minus becomes a plus. So here is minus, and this will be plus. Okay, minus 3k over m plus 3 over 2k over m squared. Okay, this is in terms of omega, and you can see omega to power 4. We can use that omega squared equal to lambda. Lambda is called eigenvalue. Okay, now you notice the difference between omega n or native frequency and eigenvalues. This is mathematically called eigenvalue, which is the one that you found in linear algebra. Okay, in terms of eigenvalue, it is lambda square minus 3k over m lambda plus 3 over 2k over m square equal to 0, which is a quadratic in lambda. And this equation is also called characteristic equation, in which you can find the roots. Okay, so there are two roots because this is quadratic. There are two roots. of lambda, and then you can get back omega. Omega is always positive. So when you get omega, you will take the square root of lambda. And when you take the square root, it's a plus minus, but we don't take the minus because omega or the nature frequencies are always positive. Okay, so solving using the general equation, you get the equation, you get the values of the eigenvalues, which is lambda 1 equal to 0.634 k over m, and the lambda 2 is 2.366 k over m, and then you take the square root to get natural frequencies in radian per second. Omega 1 square root of lambda 1, square root of 0.634 k over m, and omega 2 is square root of lambda 2, square root of 2.366 k over m. The numbering is important here in vibration. We should number from lowest value, that lambda 1 is the lowest. Lambda 2 is the second highest. Okay, so this will be lowest frequency, lowest value, and this is the lowest frequency. Okay, then the bigger one, the second bigger. So for 2 degrees of freedom, as you can see, we found 2 natural frequencies. That is, as we said in the beginning, that the number of degrees of freedom and the natural frequencies are equal. The number of natural frequencies equal to the number of degrees of freedom. Now let's go back to A1 and A2. A1 and A2 cannot be found because there is infinite number of solution here. If you put omega equal to omega 1, there are 2 values for omega. If you put omega equal to omega 1, you will find many solutions for A1 and A2. If you put omega equal to omega 2, you'll find many solutions for A1 and A2. So what you can do, those 2 equations here, find from those 2 equations, find the ratio of A1 and A2. So A1 over A2 from the first equation equal to K over 2K minus omega square m. And from the second equation, A1 over A2 equals to 2K minus 2 omega square m over K. In fact, those are equal. And this is why we get infinite number of solutions when you put omega equal to omega 1, okay? And you will find, so we put the ratio rather than finding how much is A1 and A2. Okay, the 2 expressions for the ratio of the amplitudes are found as A1 over A2 equal to K over 2K minus omega square m, which is also equal to 2K minus 2 omega square m over K from the second equation. This is called amplitude ratio. Okay, the meaning of the amplitude ratio, you can find the value of A1 and A2 from the initial conditions. And this will be part of the response to find the response. Okay, so the amplitude ratio for the first natural frequency when omega equal to omega 1, we find that A1 over A2 equal to K over 2K minus omega 1 squared m. And when you substitute for omega 1 squared, you will get a numerical value equal to 0.731, which is positive, as you can see. For the second natural frequency, when you put omega equal to omega 2, the amplitude ratio becomes minus 2.73, which is negative. This is positive value. This is negative value. And this has meaning. I will talk about this next time, inshallah. Okay. On Tuesday we will continue this lecture.
دكتور عندي سؤال في الليكتشر. دكتور قبل شوي انت قلت الناتشرال فريكونسي مال السيستم بيكون 1. شلون
إيه؟
بعدين طلعنا كل واحد؟
شلون مرة ثانية أقول؟
قلنا الناتشرال فريكونسي مال السيستم بيكون سيم يعني.
إيه؟
وبعدين شلون طلعت اوميجا 1 غير اوميجا 2 غير يعني؟
اوكي. انا لما قلت لك ان system will oscillate with the same frequency, it will oscillate with the frequency omega 1, or it will oscillate with the frequency omega 2, or it will oscillate with both. If the system is oscillating with the first mode, okay, I didn't talk about the mode yet, huh? But when it is oscillating with the first mode, it will oscillate with omega 1 only. There is no omega 2. And if it oscillates with the second mode, it will oscillate with omega 2 only. If you give initial conditions that will have the mix of the two modes, the system will oscillate with the two natural frequencies at the same time. When I said that they will oscillate with the same frequency, I meant all the points on the system will oscillate with the same frequencies. On the diagram here, all the points, any point on the system, you know, here or here or here or here, if this is oscillating with the first mode, all the points here, you can number them 1, 2, whatever, okay, up to 10, whatever. This will oscillate with the same frequency omega 1. If the system is oscillating with the second mode, all the points on the system will oscillate with omega 2. If the system is oscillating with the mixing modes 1 and 2, all the points will oscillate with omega 1 and omega 2 at the same time. Okay, this is what I meant by same frequency, that all points will oscillate with the same frequency, not with one frequency, with the same frequency. So it can be omega 1, it can be omega 2, it can be both.
اوكي دكتور مشكور.
Okay. I will see you today at 4. Right? At 4 we said the quiz, right?
Yes دكتور.
All right. Yeah. مع السلامة.
مع السلامة.